we will now see how we can perform writes in a sequentially consistent machine. And more specifically, how to detect write completion. Recall what write completion means. It means that no other thread or CPU can read the old value of the variable that is being modified. And the CPU which wants to modify a variable, it has all the information it needs, which is simply the address and the data, but it is not allowed to do the next memory access before this write has completed. So it must know when it has completed so that it can proceed with other things. And you can think of this as an ACA program where the CPU and cache is one actor and memory is another. Okay, depending on if it's bus-based or much larger multiprocessor, the memory will be distributed to different nodes. But for this, conceptually, it's sufficient to think of memory as one actor. Okay, so the CPU then sends a request. Well, actually, it's not the CPU, it is the cache, because the CPU just puts the data to the cache, but the cache is the one which discovers that it doesn't already own this variable, so it has no permission to write to it. Okay, so the cache will send a request to memory and request permission to write to this. Okay, so the memory gets this request, this message, and the memory knows which other caches have a copy. So it can tell these caches to remove their copies. And by removing the copy, it simply means that it should mark it as invalid, which in turn gives a cache miss if that CPU would like to read the variable. Okay, so the memory either sends invalidations or updates, but let us focus on invalidations. I will comment on write update later, but we will not go into that in particular detail, just noting that it's a little bit more complicated. Okay, so the receiving caches of these invalidation commands or requests, they must reply so that the memory knows that they have removed their copies. And then when all of them have acknowledged that they have got the invalidation, the memory can reply back to the CPU which wanted to write. And when that CPU has got the acknowledgement from the memory, it can proceed and do the next memory access. So what we want to achieve is write atomicity. And there are two problems. First, that writes to a particular memory location should be seen as the same sequence of writes, I mean the same data to a certain variable should be observed by all the CPUs. That's one thing. And the other thing is that no CPU should be allowed to read the data that has just been modified before the write has been completed. And how could that happen? Well, if during this collecting of invalidations and acknowledgements, there is another CPU that did not have a copy, which wants to read this. And if the memory would allow that read to proceed, then we have violated the second point here, since it would allow reading of the modified value before the write had completed. So that is not permitted. Okay, so how can the writes be serialized? Well, it's very simple. Suppose 2 or more CPUs want to modify the same variable, and they will send these write requests to the memory, and clearly one of these requests will arrive first, and that one will be accepted, and the others will get a reply, try again later. So they are not queued in any way. That would be impossible, because that queue could be of any size after a while. It's much better for the memory just to say try again later. So that is what will happen. And eventually it will succeed, hopefully. Well, it will. Okay, and the other thing, reading the modified value. Okay, so what is the problem? If this T2 would read the value of A before this write had completed, then it could start doing this write, and these two could, the value of B could reach T3 before the value of A, and the program would be wrong. So how to do that? Well, it's the same. Namely, that if any CPU wants to read this while the memory controller is collecting these invalidation acknowledgements, then it should simply also say try again to that cache. As we will see, there are different so-called states of an address. Either memory block state, state in the memory, or states in, another set of states in a cache. And in the memory, a cache block or memory block can be in a so-called transient state. And that is a state which is temporary and will be resolved to go into a more permanent state, which of course can change in the future. But while a memory block is in a transient state, all irrelevant requests are rejected by being given a try again reply.